we're going to discuss the controlled gates, so in particular two types of controlled gates. One is the controlled NOT gate, also called the CNOT gate, and the other one is the controlled Z gate, the CZ gate. And both of them have, because of their structure, they have conditional logic in them. That's what the controlled part is. And we're going to go over it one by one. So here is the CNOT gate, controlled NOT, and how it's diagrammed. And written out here is how it works. If qubit 1, and we remember qubit 1 is this one, qubit 0 starts here, then qubit 1 is in the 1 state, then apply the NOT operator to qubit 0. So if qubit 1 is in the 1 state, apply NOT operator on qubit 0. Let's see that on an example. So here we also write it out, CNOT for 1, 0, meaning control is the first gate and 0 is the gate that it acts on. If we apply it to the 0, 0 state, nothing happens because the control gate is in 0 state. Same for 0, 1, right? So this is still in 0 state, so we're not going to see any effect. But now, if we apply it on the 1, 0 state, one says now apply the NOT operator on the 0th qubit. And if you do that, that will turn into the 1 state. So we have the resulting state 1, 1. And now if we do the CNOT operation on the state 1, 1, then we see exactly what we would expect. The 0th qubit turns from 1 to 0. Now we're going to discuss the controlled Z gate, and that is very, very similar, except for that is actually symmetric. So for example, if qubit 1 is in the 1 state, then we apply the Z operation to qubit 0. And we remember the Z operation also has a condition in it, so it will do a phase shift, but only if that qubit is in state 1. And so this is actually, both of these states are basically control states, so that's why this is actually a symmetric operation. So let's have a look at what that looks like on the 0, 0 state, obviously, because the controlled qubit is in 0 state, nothing will happen. Same for 0, 1 state. Now, for the 1, 0 state, the control qubit is 1, but now it means operating the Z operator on the 0 state of the 0th qubit. And that only has an effect if that's actually in state 1. So here we also don't see an effect. The only time we do see an effect is when both of these states are 1, right? So the control gate is 1, and now we're acting the Z on the 0th qubit, and that causes the phase shift, or in our case, basically we represent that as a negative sign. Now with these two controlled gates, let's do an example. So we have a circuit here with 3 qubits, and we count them as the 0th qubit, 1 and 2. And you see there's a NOT operator, there's a controlled NOT gate here, and afterwards there's a controlled Z gate. And let's explore how certain states are manipulated by this circuit. So let's enter the state 0, 0, 1. And we're applying the NOT operator on the 2nd qubit, and that's this one here, the uppermost one. And what that does is it basically changes the 0 state into the 1 state. Now comes the CNOT operation. CNOT to 1. 2 is the controlled gate, 1 is the control qubit, 1 is the qubit that it's acting on. Now we have the control gate being 1, meaning the NOT operator is applied to the 0, and that turns it into a 1. And so we have the resulting state 1, 1. And now comes the controlled Z gate. The control Z gate finds the qubits 1 and 0, both in the state 1, and that means we add the negative sign to this state. Let's do one more example. We bring in the 1, 0, 0 state, and we apply the NOT operator on that 2nd qubit. So again, 0 first and second qubit, which will make that into the 0, 0, 0 state. Now we apply the controlled NOT gate. Now obviously that doesn't do anything because the control qubit is 0. And now we apply the controlled Z gate. And again, because the control qubit is in 0 state, nothing will happen and will end up being in this state 0, 0, 0. Okay, that brings us to the end of this video. Again, I hope you found this video helpful and look forward to seeing you and